So, hello everyone. I am Dibyajyoti Mukherjee from Indian Institute of Technology, Delhi, Electrical Engineering Department. So today I am going to present my sensor related paper, that is a system level demonstration of low frequency magnetoelectric power transfer system. So this presentation consists of this following topics: background, introduction, design, circuit level result, and conclusion. The first one is the background and the motivation. Means why we started doing this type of researches. The motivation is like magnetoelectric is different from the conventional antennas and the different type of power transfer techniques available. How? Like the normal conventional wireless power transfer technique, first one, the RF, that uses high frequency based radiation. And for that reason, we can miniaturize the size. But with high frequency radiation, there are some issues like a lot of absorption in the watery media and different soft tissues and all. And with the coils or loop antennas, there is another problem, that is the misalignment. Otherwise, it is very good antenna for power transfer and other application. And the third one is the traditional magnetoelectric devices, how it started. Like initially, Professor Nyang Sun, who actually first reported this type of antennas, he made this on silicon and then fabricated this thing based on FEGA-B and ALN. He uses a bulk size DC magnet, and again he used the high frequency region for operating these devices. But the entire device need to be encapsulated because the material they have used, that is not completely biocompatible. So we are targeting these issues in our design. So the magnetoelectric wireless power transfer works on the principle of like conversion of magnetic field. Like it consists of different layers, the magnetostrictive layers, which is responsible for sensing the magnetic field, and then it converts the periodic strain to the underlying piezoelectric layer, and from the piezoelectric layer, we can receive the time varying voltage. So this is the principle of magnetoelectric wireless power transfer. Instead of the electromagnetic resonance, it works on the acoustic resonance, so, and that's how we can reduce the size of the antenna by multifold, multiple magnitudes. And this is the structural analysis that we have made. We have made our antenna that works at a resonance frequency of 50 kilohertz, but still its size is limited to few millimeter. And that is one interesting point. Like usually 50 kilohertz, if we consider in RF scale, the size would be like few kilometers. So these are the FEM simulations that we have done using COMSOL multiphysics, which shows that at a particular frequency of 9.9 kilohertz, it is showing highest strain. That's why we chose this particular mode. And this is the fabrication process. We have used the made glass layer, then bonded a layer of epoxy, and then the piezoelectric layer PVDF, and again another made glass layer. And from top of the made glasses, top and bottom side, we have taken the electrodes. And then after that, we have encapsulated it with biocompatible material Perylene C up to 5 micron, and then encased the entire thing inside a 3D printed PVC tube. This is the magnetoelectric test setup that we have in our lab. It consists of a pair of Helmholtz coil, an electromagnet, and some lock-in amplifier and oscilloscope to record the voltages. And based on that, we have measured the frequency response of the device, like with sweeping frequency with different magnetic field. It shows that the resonance is around 50 kilowatt. That's why we're getting the highest voltage around the same point. And also the power profile across 8 kilo ohm load, we are getting the optimum power. And with different magnetic excitation, it is increasing. And this is the radiation pattern measurement that we have done. Like unless means the process is similar to the traditional antenna, but here we cannot do the far field measurement because of the size of the antenna, the electromagnetic resonance that is different. So we have done the near field testing with a planar coil, and these are the radiation pattern in the azimuthal plane and the elevation plane, which resembles the similar structure that is with the loop antenna or the dipole antenna. So it has a resemblance with the loop or dipole antenna, but it has better performance in terms of the misalignment. Like with misaligned condition also, you can see the deviation is up to 15 to 20%. So that is better, we can say, compared to the traditional one. And these are the other spectrum with the different magnetic field we have taken, and also we have measured the limit of detection, like up to what means up to the minimum magnetic field, what minimum magnetic field it can measure. So as per our result, it can record up to few micro oersted magnetic field, and in the higher range, it can go up to few Teslas. And we have also used another interface power management circuit. We have designed and developed this circuit in our lab. And this power management circuit consists of some buck converter, some regulator, some DC-DC converter. It basically extracts the time varying voltage and generates a stable DC voltage from a range of 0.7 volt to 5 volt. It works, and the current consumption is as low as a few 1 microampere, and it actually generates a stable 2.5 volt supply. And the overall area it consumes, that is up to 36 millimeters square. I know it is quite large, but we have plans of miniaturizing the entire PCB into CMOS based circuit. We are currently working on that. And these are the results that we got from the entire system, like integrating the antenna and the power management circuit. You can see that if the magnetic field is lesser than 1 oerstate, that time it cannot charge the circuit, so that it could not turn on. Like if you see the ME voltage is 500 millivolt, but the regulator could not turn on because the regulator needs 2.7 volt after multiplying also. So it is not getting the sufficient current to drive the regulator. That's why it cannot turn on. But when the magnetic field is greater than 2.7 oerstate and the ME voltage increases to 700 millivolt, that time it is able to turn on the regulator and the entire circuit is operational. And if we go on further increasing the magnetic field, we will get better performance. But we are limiting the magnetic field exposure up to 5 oerstate. That is actually allowed within the range of the human body exposure and the human ambience as per the IEEE and ICI NIRP standards. And this is the power conversion efficiency that we have measured based on this the power management circuit. And we have also compared the result of our ME system, ME WBT system, with the state-of-the-art papers. And it is within the agreement, it is within agreement with the other result that are reported by other researchers. Those are based on different systems, and some also reported the battery-based systems also. Like we can see, this is a discrete system, but still it is able to give us efficiency of greater than 85% overall. And so this is the conclusion of our work. It works at a lower frequency range within 50 kilohertz and still able to miniaturize the dimension, overall dimension, up to few millimeters. And the range of operation is up to 200 centimeter. And the sensitivity of the ME antenna is 0.5 volt per oerstate. That is good compared to the other results, other paper that we have seen. And also generates stable DC voltage from 2.7 oerstate. And in future, we have plans to implement some of the advanced modulation schemes that we know. That is we have already implemented ASK, FSK, but we have plans of implementing QAM and ASK for direct stimulation application. We are currently working on those things. And also we have plans to explore some high frequency transfer, like the high frequency data bit transfer for this type of application, where we can use it for stimulation and other detection application. So this is the conclusion and this is the acknowledgement. Thank you for listening. I have 2 videos, means if you allow me, I can share. So here it is. So you can see this is the not working. Videos will not work. We cannot run it. I think okay, it's okay now. Actually, we have shown both the ASK and FSK. The binary FSK we have tried, and also pseudo random ASK we have tried, and some other experiments are currently going on. So thank you so much.